we're looking at a group of points that has a linear trend but is not exactly linear, much like our foot length and height data, how do we know which particular line is the best line, the line that best fits the points? We do a process called least squares regression. And what this means is that you start by finding the residuals of all of the different points. So we start by looking at residuals. A residual is the distance from the line of best fit to the actual data value. So the y value predicted by the line to the actual data value. So I'm going to define residual here. Residual is equal to actual y value minus predicted y value. Predicted by the linear equation. So I come up with some sort of an equation that relates height to foot length, and if I were to plug in a person's height, say this person that has, or the person's foot length, 29, into this equation, it would give me some sort of prediction for their height. Looks like maybe about 177. But their actual height was about 185 centimeters. So the difference between the actual and the predicted is called the residual, or the leftover, or the error in the prediction. Now notice we have all different residuals here from the different size residuals for the various points, some large, some small. And each of these residuals has a square associated with it. So if we take that residual, notice that some of the residuals are positive and some of them are negative. If we were to add up all of the residuals, so notice right here I did the sum of the residuals, what we end up getting is 0. That's what this says. This says 2 times 10 to the negative 11th, which is 0.000000000002. Your calculator just can't quite round it correctly, and so what this means on your calculator is that we're talking about 0. This is the number 0. So the residuals add up to 0. So if I were going to use this residuals to determine how well the line fit, it wouldn't be terribly helpful because I could have big residuals or small residuals, but the positive ones and the negative ones will always cancel each other out and add up to 0. So instead, I do the sum of the residuals squared. I square all of these residuals, making them positive, which also serves to emphasize the bigger residuals and make them kind of stand out more as outliers. So that's what these little squares are. This comes from your calculator. You can actually find the residuals and the residuals squared on the calculator. All of these little areas, these square areas, are added up and we get the sum and we get a particular number. And so let me tell you how that number is used to find the line of best fit. The line of the best fit is called the least squares regression line, because it is the line that minimizes or makes as small as possible the sum of the squared residuals. Now you think, well, how does it do that? It turns out that there is a quadratic equation involved. The minimum amount of the quadratic equation is its vertex, and so there is a kind of a long, complicated equation that is done to determine how that line is calculated. Your calculator does that internally for you, but that's what's being done. The calculator is computing the line for which the sums of these squares is as small as possible. Any other line would result in a sum of residual square that's bigger than this. The meaning of the slope then, when you do a linear regression, it gives you slope and y-intercept and gives you some other things. We'll talk about in the next video what R means. But what does the meaning of the slope mean? And what I want you to recognize is slope is a rate of change. Specifically, the change in y over the change in x. So it's telling us every time we go up 1 centimeter in foot length, how much is the height predicted to go? So it's telling us actually a predicted rate of change. So the way we would say this, if we look at our slope here, for every 1 centimeter increase in foot length, the regression line, because that's what we're using to predict, the regression line predicts about a 2.48 centimeter, nope, not 48, sorry, 2.84, a little dyslexic moment there, 2.84 centimeter increase in height. Okay. So for every one unit change in the x direction, the slope tells us what to expect as a change in the y direction. Something else you might notice is the y-intercept is 96. This, how do we interpret the y-intercept? This wasn't really on your notes, but the y-intercept sometimes has a reasonable interpretation and sometimes it doesn't. In this case, it doesn't. Because remember that the y-intercept has an x-coordinate of 0. So the y-intercept in this case says, if my foot length is 0, my height is about 96 centimeters. Clearly not making any sense. This is an example of what's called extrapolation, where you're extending beyond the data. We don't have anybody with a 0 foot length. So the y-intercept paired with a 0 foot length doesn't make any sense. It only makes sense within the range of acceptable foot lengths. So I just wanted to throw that in. Then you'll want to look at the next video for the interpretation of the correlation coefficient R.